Over the past 5 years, humanity has begun to practice a wholly new type of astronomy, gravitational wave astronomy. Instead of looking at some form of light coming from the universe, gathered with a telescope, radio dish, antenna, or some other equipment sensitive to electromagnetic radiation, we've instead built specialized gravitational wave detectors that can detect and characterize the ripples in spacetime produced by masses spiraling into, merging with, and ringing down from interactions with one another. On September 14, 2015, our knowledge of the world forever changed with the first direct detection of gravitational waves from merging black holes. Since that event, some approximately 60 additional gravitational wave signals have been seen, including not only merging black holes, but merging neutron stars as well. The past 5 years have validated Einstein as never before, proving many of general relativity's predictions right. Over the next few years, gravitational waves will have an unprecedented opportunity to put our theory of gravity to the test as never before. Although you should never bet against Einstein, new ways of probing the universe always have an opportunity to show us that it doesn't behave how we might have expected. Here's how gravitational waves might wind up proving Einstein wrong. According to general relativity, gravitational waves arise as an entirely new type of radiation, separate from anything known before. Whenever a mass accelerates through a region of curved space, or whenever a constantly moving mass moves through a region of space where the curvature is changing, the changes to the curvature of space generate ripples, similar to water ripples whenever a raindrop falls into a pond. These ripples, however, up until 2015, this was all theory, with only indirect tests available to confirm small aspects of this. But the advances made in laser interferometry, as originally leveraged by the LIGO collaboration and later joined by Virgo, enabled us to detect the ripples in space as gravitational waves passed through the Earth. These waves, indeed, pass through Earth at the speed of light, alternately stretching and compressing space in perpendicular directions, enabling us to see these gravitational waves for the first time. As the waves passed through the Earth, the stretching in one direction caused light to require a little bit more time to traverse it, while the compressing in the perpendicular direction reduced the light travel time by an equivalent amount. With slight changes in the length of each laser arm in the presence of a gravitational wave, the interference pattern that the light traveling in these interferometer arms creates gets altered by a tiny bit. By observing the patterns that change in multiple detectors, we can reconstruct properties of not only the sources that created these waves, but the waves themselves.